All right. Well, good afternoon, everyone. Thanks for joining us. My name is Tony Guay, a remote sensing specialist with the Wheatland Lab in the School of Forest Resources. And welcome to this afternoon's Wheatland seminar. This afternoon, we have Stefan Claesson with us. He's a principal scientist and owner of Nearview, where he specializes in GIS and remote sensing applications. Stefan has worked as an archaeologist and environmental scientist in New England for 25 years. Previously, he worked as a forensic archaeologist with the U.S. Department of Defense, where he supervised Navy salvage units in the research, survey, and recovery of submerged aircraft, shipwrecks, and unaccounted for U.S. military personnel. He was also a research scientist in the Ocean Process Analysis Laboratory at the University of New Hampshire, where he directed research projects in historical marine ecology. He was the recipient of the NOAA Nancy Foster Scholarship for his research in maritime archaeology at UNH, where he received his PhD in 2008. And I just remind everyone that's attending on Zoom to please, if you have questions, just put those in the chat box and we'll handle those after Stefan's presentation. With that, Stefan.
Thank you, Tony, for the introduction. It's a pleasure to be here in person, and thanks everyone also who's joining us virtually. Nearview is a company that I started in 2015 when drones first came on the scene, I guess, and I could immediately see the potential for drones and their use in supporting environmental science and also cultural and natural resource management. Especially significance to Maine. We've got some hold on just a second, everyone. Technical difficulties.
I don't see it.
It might be waiting for him to respond to what's up top, there.
Let's okay.
And then continue.
Continue.
Yeah.
All right.
Yeah.
All right, we're back. Anything else?
Share your screen to Zoom.
Share my screen to Zoom. Okay, almost there. Share screen. Yes. All right. Okay, we can continue. So really just recognizing the potential for drones and use of in natural resource management, especially its importance to Maine with over 3,000 miles of coastline, strong dependence on marine resources, lots of coastal infrastructure. We really need tools to be able to predict and monitor changes to our environment and help make better policy decisions based on accurate information, and drones, I think, really provide that opportunity. So what I try and do is not just collect and deliver map products, but also help people to interpret the results and make management recommendations and put together some strategies around that drone data. So I'm going to talk about a little bit about drone technology and sensors, not so much about data collection and operations, and focus more on the data analysis and interpretation. I always think that flying is really the easy part. It's mostly automated. It's really what you do with the data that matters. So what I'm going to do is, I guess, kind of throw the kitchen sink at you today. I'm going to talk about, present 4 different case studies. I'm going to start with the most basic documentation, grammetry, structure from motion, of a archaeological site, and get a little bit more in depth into measuring volumetric and change on beaches. Also talk about detection of invasive species using multispectral sensors and some machine learning classification tools like random forest, and also talk about classification and biomass estimation of intertidal seaweeds, also using multi as well as hyperspectral remote sensing tools. So the first case study is of a shipwreck, which received a lot of media attention and made national news back in 2018, following a powerful nor'easter. And with all that media attention, there was a lot of tourists, a lot of sightseers who wanted to see this wreck. So there was concern from the locals, not just about the erosion that was occurring to the site, but also vandalism. People were even going down there with chainsaws, trying to take pieces off the wreck site. So a lot of local concern. Also, you know, the state agencies and other local people wanted to know the historical significance of the site. It was often referred to as a Revolutionary War era vessel. Some folks even thought it was a Viking ship. So the goals of our project were to first identify who does it belong to. Is it a state of Maine property? Is it municipal? Is it private property? And is it eligible for the National Register? Again, its historical significance. And trying to get there, what sort of methods could we use for accurate documentation, being cost effective and doing some rapid deployment.
Where was it?
So yeah, so the site is in York Beach, Maine, Short Sands, a very popular summer destination. Most beach goers are completely unaware of the site. And again, in that February 28th storm, there was probably around 6 feet of vertical sand loss on the beach. So during high tide, the surf zone, the shipwreck's just getting pounded, and at low tide, it's completely accessible, so people can go right out to it. It's not the first time this wreck was exposed. It's been exposed numerous times back to 1958. But what is notable is that the frequency of those exposures are getting shorter more recently. So there's actually a couple exposures that I don't have documented here, which was in 2011. So initially it was like 20 years, and now it's down to like every 7 or 10 years this shipwreck's getting exposed. So when it does get exposed, what do we do? And so our solution was, of course, to deploy unoccupied aerial systems, or UAS. Again, just using your standard Phantom DJI drone, collect a number of digital images across the site. This is an orthomosaic of a little over 50 images. So, but we do get less than 1 centimeter pixel resolution across the scene. We also use the GNSS GPS receiver on the drone, as well as a rover on the ground to get really accurate geolocation. So unfortunately, when we finally got to the site and got contracts in place and permissions to go out to the site, most of the shipwreck, nature did its thing and covered it up with sand. So when we got there, the only thing we could see was the frame ends of the ship. But there's still a lot of useful data that we could get out of the site, that the portions that were exposed, and the beach elevation data here. So now we have accurate point elevation data across the site. If a storm event occurs in the future, we can know precisely how close to exposure we are. And this also supports beach restoration efforts to ensure that the site isn't damaged if beach nourishment is necessary. Obviously, we also get good baseline measurement information, start to know a little bit more about what was this ship, its length, its width, And maybe we can tie that to some historical records, which we have been able to do for this site. Taking it a step further, what we wanted to do was to make sure that our, this big photogrammetric data, how do we manage it over the long term, and how do we make it accessible to non-GIS users? And so we stored this data set in a cloud-based GIS system. And we collected a number of wood sample species IDs across the site, and also collected dendrochronology samples from the rec site. So this type of data management system is really useful for adding, annotating data, taking measurements. Just for example, we initially collected 2 dendro samples from the rec site planks, hull planks, and those turned out to be birch and beech samples. And the tree ring lab at Cornell University said this is great, but we would really like an oak sample because we have a good chronology to Eastern Mass oak. So can you go back and get another oak sample? Well, okay, so 1 month later, the rec is covered up even more, but we have this great GIS system where we know the precise location of all the timbers we sampled. So it was very easy to navigate back, locate that timber, even though it's buried, dig down and sample what we needed to. So this is just a before and after of that red oak frame that we ultimately sampled. And with the birch and the beech and the oak, we've had a pretty good fit to the Eastern Mass oak chronology, giving us a felling date of around 1753. And this chronology, the felling date is 1753, but now we have tree rings going back to the early 1600s. So I always like to think of these shipwrecks as important environmental warehouses as well, and how they might contribute to regional climate studies. So for historical research, I think we were also very fortunate to have a very detailed records of shipwrecks that occurred in York in the 18th century. This one in particular documents the sloop Defiance, which was sailing from Salem, Mass to Casco Bay. It went ashore, recorded at York Beach in 1769. It was carrying a small crew, some flour, pork, and some English goods. And it states that it was pushed ashore during the storm, and most of the cargo was saved, and the crew was saved, but the ship was bilged and lost. So we had a very good reference point there. And with our dendrochronology and our site history, we now know that this was not Revolutionary War or a Viking ship, but a pre-Revolutionary War, probably built around 1754, identified it as the sloop Defiance, which wrecked in 1769. And because of its early age, it is eligible for the National Register of Historic Places. So with the accurate geolocation, we know that the wreck is actually owned by the town of York. It's not a Maine state submerged resource. And now we have the baseline measurements to be able to measure and document change over time to that site. And so again, one of the goals was to come up with recommendations and best practices for whenever these wrecks get exposed on our beaches and our shorelines. We want to provide a rapid response, how to do as little impact to the site as possible, and use methods that are repeatable. And so that's using drones to do that, get that high resolution, using wood sampling to help identify the ship, where it might be from and its age, and then get into any detailed documentation, and that can all be housed within the sort of this cloud-based GIS system. And this would be an approach that, again, is applicable to other intertidal and beachfront sites. So moving on to our second case study, I'm going to stick with beaches. This was a project that was headed by the Maine Coastal Program and Maine Geological Survey between 2018 and 2020. It was a mapping project to quantify sediment movement over time, seasonally and annually, and quantify changes in volume on a group of beaches, with the goal of really improving the longevity of beach nourishment projects. Where's the best place to put dredged materials? Where's the best place to put sand for beach nourishment? So I worked with them on 3 study sites in Scarborough, Saco. Everyone's probably pretty familiar with Camp Ellis. The place seems to get wiped out every winter, and Wells Beach. So it's actually pretty difficult to map beaches because you have to cover some shallow zones and surf zones, and most people think of beaches just as like the upland portion of it where beachgoers hang out, but it's a much wider zone. And so to survey that, we used a number of different technologies. For the onshore areas, we used, of course, the drone. Again, this is photogrammetry, structure for motion. This drone is a DJI M600 with a high-end camera, a Sony 42 megapixel with GNSS GPS. So that covered the onshore areas. Then for nearshore, in sort of that surf zone area, the Maine Geological Survey used a single beam echo sounder mounted onto a jet ski, so a pretty novel survey approach. And then for offshore areas, the Maine Coastal Program used their research vessel, the Amy Gale, with a multi-beam sonar system. And so the goal of those different surveys was ultimately to fuse them together to create a continuous surface. So basically fusing together the onshore, the nearshore, the offshore, and do this for each season over 2 or 3 years. So the white lines that you see in each location are some profiles, which I'll show in the next slide. Just to show how dynamic a single beach can be. This is more of a natural, the Bayview profile, a natural dune system, which provides good coastal protection. And then as we move south down to Camp Ellis, we can see what a hard seawall, riprap, revetment beach profile looks like. And when those waves come in, they hit that wall and just drive the water downward and erode out the beach. So once we've generated these surfaces over time, we can start to measure volumetric change. So on this map, the red colors are indicating areas of greater loss, and the dark blues of where sand is being gained. This is from fall 2018 to summer of 2019. And so what you can see right away under volume changes is that there seems to be gain onshore, but loss offshore with a very small net gain. So what's happening onshore isn't going to provide a good picture of what's happening offshore and vice versa. So this is really important for monitoring and having baseline studies. You don't want to just look in one short time period. You really have to look at a longer time series. So this would be another season in 2019. Pay attention to actually let's go back one slide here. Camp Ellis, which is on the right-hand side of the slide. dark blue area where it says gain. So that particular season, there was a beach nourishment project right in front of Camp Ellis. So one season later, that's completely gone. So it doesn't take long at all when you have hard shoreline for that material to quickly transport, either offshore or down the beach. Here's a one-year period from 2019 to 2020. Again, the importance of looking at these volumetric changes over time. If I go back again, you'll see we have this big loss in sediment. And then going forward, one season, we've got a big gain. So again, looking at those longer time periods. And here we have the fall 2018 to fall 2020. We can really see get a little bit better picture of what's happening over the long term, where things look kind of drastic over a couple seasons, but over time, things maybe aren't so bad. And we can really see where sediment is being transported, where it's being lost and gained over time. So the applications, again, are beach nourishment and dredging activities. Want to know where the optimal places to put sediment to ensure the longevity of those beach nourishment projects. And then for dredge activity and disposal siting, how might they best support beach nourishment depending on where they're placed, and also making sure that they don't impede any navigational channels or anything like that. There was a report put out and it's published on Digital Main. So if you want to have more information on that study, it's publicly available. So another great application of UAS is the detection of invasive species. This is a project that involved mapping water chestnut for a conservation group called OARS, which is the organization for the Assabet River down in Massachusetts, not a main project. But so our goal was to map and automate the detection of this aquatic species. It's a real nuisance. This view right here is of a water reservoir in Framingham, Mass. All that green stuff that you see is water chestnut. And when we first started this project, the water authorities, well, we know it's a problem, but we're not really too concerned about it. But after sharing some of this imagery with them, they said, okay, we see now that this is really something we need to tackle as soon as possible, because these reservoirs, those seeds, that water chestnut is starting at the reservoirs and going downstream. So it's almost an impossible battle for these conservation groups downstream to try and manage these invasive species if you can't really get to the source. But what we tried to do was do a little demo or pilot study for them to show how machine learning and random forest classification could automate this process of detecting the species that they're concerned with, and then they can hopefully come up with some mitigation measures like spraying or manual removal of them, and target those areas that are really infested with the stuff. So this was a project actually back in 2017, 2018, just some of the apps and software that was used in the process. My go-to photogrammetry software continues to be Pix4D Mapper for processing just color imagery as well as multispectral. And Pix4D is also now getting the capability to process snapshot hyperspectral data as well. So that's a really useful piece of software. And then using ArcGIS and some R scripts for machine learning algorithms and it's not on here, but Envy as well. It's a great tool for imagery analysis. Some of the flight parameters and site locations. So this was the multispectral sensor was a Parrot Sequoia, which is now Mica Sense. You might be familiar with the Red Edge camera systems that they've become known for. But this was in the real early days, and I had this Phantom 3, and I had to like wire tie and rubber band this thing on to keep it from vibrating apart. So, but we got it to work, which is great. And it has 4 narrow bands: green, red, red edge, near infrared. This first generation Parrot Sequoia. So these are ortho images of those narrow bands, and then the redder ortho is an NDVI ortho. So for ground validation and to build that machine learning model, we could use what I call visual ground truthing. We've got high resolution imagery of the scene. And so we can zoom in a little bit, and areas that we're sure are water chestnut or something else, we can identify that. But we did want to get on the ground, and so the conservation group went in and helped us identify a number of different species within that area, which we could use as essentially training data to train our model, and then classify pixels to create a map and show us where that water chestnut really is. So for the training data, we create a bunch of little polygons over the scene for all the different native and invasive species that we're interested in. And then we get the actual output, which performed really well. So the green areas, obviously the blue is water. The green areas are the water chestnut, and the brown represents dying water chestnut. This was an area that they had actually sprayed to kill off some of that water chestnut. So this is really helpful to them because it gave them information to know how well their mitigation strategies were working. Okay, so we covered a lot of it. This was completely choked in with water chestnut initially. So they killed off a lot of it, but there's still some patches left, so that now they could go back to those trouble areas and try and mitigate that or remove those manually. One tricky bit was distinguishing between water lily and water chestnut. If I go back here and looking at the map, it's very hard to distinguish water chestnut from water lily using the ortho imagery. And then when we go to classification, we can really see the distinction between water lily and water chestnut. Water lily being the yellow, which is native, and want to keep that in place. And of course, one of the things you always want to do is let people know how accurate your map or your classification is. And one of the ways that I do that is through what's called a confusion matrix. And that's looking at how accurate the actual map is to the predicted, I guess, pixels. And so the diagonal shows all the correct pixel classification, and then you have errors of omission and commission. And you can see overall we have very good accuracy. So the kappa is going to be the overall accuracy assessment, so 97% accuracy overall. But you do want to look at all the different classes of information, and most of them are pretty good, but you can see that there's some issues with burr read that's a little bit lower here. Same over here. So you got user accuracy and predicted accuracy. So over here with burr read, so 77 pixels that should have been buried, were misclassified as trees. And then if you go the co-mission direction here, we've got 48 pixels that should be trees, but were misidentified as buried, if that makes sense. The one thing that we haven't done yet is to validate this model on other areas, other survey areas, which we'd like to do, but the conservation group doesn't have any follow-up funding for us to do that work. So I think we've really shown in this demo the capabilities of these simple UAS tools and algorithms to do this kind of work. So what we'd like to do in the future is to develop spectral libraries and training data for invasive species, and then really the algorithms so we can rapidly and reliably automate the mapping of those both invasive and native species distributions. And then the next step would really be to develop a platform for conservation groups, water authorities, so that they can monitor ecosystem health and water quality over time. And that's a little bit more challenging, but that's something that hope to get into in its relation to the next project I'm going to talk about, which is intertidal seaweeds. So this is a project that we're actually right in the middle of. We're looking to use UAS and multi and hyperspectral sensors to map seaweeds in the intertidal zone. Working now in Maine, but hope its application will extend beyond Maine. Seaweeds have actually gained quite a lot of attention and popularity of late. This is just a little clipping that I took from my wife's Martha Stewart magazine. I confess I read it too. But so it has so many uses, seaweed, and it's entering into a lot of products. But I think one that's even really gotten a lot of attention is the use of seaweed for feed for livestock. And the reason being that seaweed may reduce methane output from livestock. I think the methane output, livestock account for about 15% of methane output globally. So this is a pretty big deal if that can be reduced just by giving them a little bit of seaweed. But I feel like we kind of need to pump the brakes on that idea a little bit. You know, as humans are really good at fishing down the food web. You know, you start with whales and then go to halibut and cod and herring and shrimp and urchins, and now we're actually down to the habitat. So we're harvesting the habitat, which I think can be kind of a dangerous thing. Especially when we know how important this intertidal zone and seaweeds are, certainly for a number of reasons. They provide storm protection, shoreline stabilization. We know that they're probably a significant source for carbon sequestration. And they are also forage grounds and breeding grounds for fish, and also fish that are commercially valuable to us. They're under a lot of threats as well by coastal development, sea level rise, coastal erosion, and seaweed harvesting potentially as well, if it was to go to this scale where we're trying to feed all the cows in the world with wild seaweed. So something to be concerned about, I think. So to manage this resource, the first thing we really need to know is where it is and how much do we have. So our solution is, of course, to deploy drones with multispectral sensors to map the seaweed beds, the areas, and estimate biomass. And we'll do that by developing spectral libraries and training data, just like in the last case study, to classify and map. We're interested in two particular species right now, Ascophyllum nodosum and Fucus vesiculosus. So ultimately, we want to be able to use drones to cover local seaweed beds, but then scale that so we can to say satellite imagery, so we can perform more regional and statewide estimates of seaweed. And this was this ongoing project was initially funded through a Maine Economic Improvement Fund, small campus initiative, headed up by Maine Maritime Academy and Schoodic Institute, Bigelow Ocean Labs. We've now been able to leverage that project and acquire a phase 1 small business innovative research grant from NOAA. And so that project is now involving those groups, as well as University of Vermont and University of New Hampshire. And so just to, I guess, set the stage, I got a short video just to give you a little bit more context about the project.
Ascophyllum nodosum is the largest percentage of the commercially harvested seaweeds. And to have good management practice, it's good to know how much you have, so you can know how much you can sustainably take and leave enough for there to be actually an environment for all the other beasties who use rockweed to, live. With a changing climate, some seaweeds are going to do pretty well and some seaweeds are not going to do well. So it's good also for us to just start understanding how much there is here so we can start tracking what's gaining and what's losing. In times past, if people want to understand how much rockweed there is anywhere, they're sending a crew of people out with scales and with quadrats, little squares to measure how much seaweed is in one of those squares, and then sort of multiplying that by the area in which they happen to be studying. And so to do that for the coast of Maine, where there's over 3,000 miles of coastline, it just becomes exceptionally challenging to get good estimates of how much seaweed there is along the coast. Having the ability to measure rockweed along the coast of Maine, to use drone technology, for me it's important because we can start looking to see how distributions are changing through time with a changing environment, with heating Gulf of Maine, and with changing chemistry, so that we can understand how to change maybe some of our management practices around harvesting.
So I think an important takeaway from that video is the difficulty of the ground validation scheme that we currently have. It's just impossible to cover the entire coast of Maine with the traditional way of doing things. And so that's where drones can really supplement, and then hopefully we can scale it out so we can get to regional and statewide assessments and be able to do that on an annual basis. Just so you have a better idea of what these two seaweeds look like. Asco, also known as rockweed, and Fucus, otherwise known as bladderwrack. So those are the two seaweeds we're really trying to tease apart. They're both part of the same brown seaweed family, but you can see the rockweed is a little bit more stringy, and the Fucus is a little bit more frilly. So there's some texture differences and also density differences as well. So I can't go into too much depth here on because we're right in the middle of this project, but did want to at least share with you some image segmentation work that we've been doing to define the edges of the seaweed beds. And so image segmentation involves creating a bunch of pixelated objects and then masking various backgrounds to try and really isolate the seaweeds that we're interested in mapping. So to do that, it's a sort of iterative process of masking upland areas, water, rock, sand, any other no data values, and then also classifying the algae with various thresholds as well. So in the upper left panel is a color image of an area that we've surveyed. This is Beals Island at the Down East Institute. On the right top is a color infrared, and the two bottom panels are NDVI, normalized difference vegetation index, and normalized difference water index. And those are indices that are derived from the 10-band multispectral system that we've been using to document seaweed beds. And we've actually we've mapped, I think, 8 different locations along the coast of Maine now, from Casco Bay all the way up to Cobscook Bay. So we have a good variety of locations and substrates to help build our model up. So the top panel is, again, the color image. It's a little dark, and the bottom is the color infrared. It's the same scene, just a different way of looking at it. And this is just what that segmentation looks like. And you set certain tolerances to expand or contract those segments, and you see what works for the objects that you're interested in mapping. And then it's a matter of masking out those things that you're not interested in, like areas of no data, upland areas. Here we used a shoreline product from NOAA, which is continuously updated. So that was useful for masking that. We used our NDWI to mask water. And then those thresholds to mask out the sand and the rock. So then we're really isolating down just those seaweed beds now. And from there we can, classify the 2 species and other species that might be in that bed. So here the red is the asco or the rockweed, and the green is the fucus. So that multispectral sensor and the segmentation approach is really doing a pretty good job at isolating our area of interest and then separating out some of those species. So now we have to go about, validating this approach and applying it to other areas and see if we get similar, effective results. We're also looking at the relationship of reflectance with biomass. So here we'd be using, can we use the drones to estimate biomass? In the field, we're using what's called a spectroradiometer to map spectral signatures of the various seaweeds. And we have found that there is a relationship between canopy depth and reflectance. And using indices such as NDVI, we can look at density as well, and vegetation health. And we are seeing a pretty interesting positive relationship. So we can map biomass using drone imagery. So in the graph, the bottom value is wavelengths, and then we've got percent reflectance. And so ASCO 1 is in the lab is about a 2 centimeter thick bed of seaweed, and then we increase it every 2 or 3 centimeters for the following ones. So you can see that reflectance increases with the depth of the seaweed. So again, the difficult piece is going to be scaling all this ground validation, lab data, first to drone imagery, but bigger challenge to scale it to satellite imagery. And our ultimate goal is to build that platform, hopefully with NOAA SBIR phase 2 money funds, so that we can have that platform for all stakeholders who are concerned about this resource to be able to access the information they need. So I guess stay tuned on that. So my goal today was just to hopefully inspire some of you to come up with remote sensing solutions to tackle some of the many environmental issues we are facing right now. Our coastal communities in Maine, seaweed harvesters, resource managers, policymakers, all desperately need accurate information right now to make good decisions. And to me, there's nothing more powerful than a good map to do that. So thank you for your time and for listening. And I'm happy to take any questions folks have. And if you don't have a question now, you can always email me at a later time. Thank you.
Great, thank you very much, Stefan. There'll be questions on the Zoom.
Here comes chatting. Are you able to see the chat?
Not right now. Let me, oh, I did something. I stopped sharing. I guess that's maybe okay. All right. I can see. Yes, I can see the chat. So the question is, are there slightly more low-tech ways to use drone imagery if you don't have access to sensors or a drone with PPK, RTK? Yes, absolutely. Most drones already have an onboard GPS, and you know, your basic DJI Phantom 4 Pro it's just an amazing little drone, and you will get very good relative accuracy using that system. It might not be, you know, great for absolute accuracy and pinning it to the earth, but you would have good relative accuracy. So it just really depends on, you know, what you want to use it for. And you could also just use a rover, GPS, GNSS GPS rover to map points on the ground. You don't need that high-end GPS sensor on the drone. You can just use points on the ground, map those, and use those as ground control points to get really good absolute accuracy as well.
You can do a lot of this stuff with your, you know, building the 3D models with a true color camera without having all the spectral advanced stuff.
Absolutely, yeah.
I have a question. Have you done much work in the realm of AI in regards to image classification of drone imagery?
Yeah, so depends on what you call AI. I think of AI as sort of an umbrella for both machine learning and deep learning. Yeah. So we are going to be working on some of that for the Seaweed project. But in each case, deep learning, machine learning, they still need training data. They still need data to build models. They're not, when I think of AI, I think of something that can make decisions on its own, learn from its own mistakes and make decisions. But I don't think we're quite there yet. But for deep learning, yeah, like I've done, build those training data sets. I haven't applied them yet to any particular case study, but I think that's the way things are going to go in the future for sure. They just require a lot of computing power right now as well.
And Stefan, have you done any work with fixed wing drones? So you're, you know, thinking of these long shorelines would it be advantageous to use those rather than the rotor-based drones for those types of applications?
Yeah, for sure. If you're using multispectral sensors as well, because they can collect imagery at a pretty high rate of speed. And that's the problem with the fixed wing, is that they usually fly out only one speed. So that would work, but if you wanted to do LiDAR or some other application, then you're gonna run into trouble with that high flight speed.
Right.
But for, yeah, corridor studies, long beaches, multispectral, or yeah, it should perform pretty good. It's just going to be the application, really. That's the driving part of it.
Sure.
Yeah.
Another question on chat.
What is a reliable and lower priced GPS for GCPs? Well, so you can probably get a pretty high precision rover system for around $8,000 right now, and that would be using a cellular network. So you'd have to be within range of a cell system, and then hopefully the state you work in has a free correction that you can have a subscription to. Maine has such a system, Vermont does as well, Massachusetts does, New Hampshire does not. So you can get away with probably $8,000 will get you a high quality GPS rover system.
DJI is not being able to fly a federal plan. The other, that seems like your projects with coastal areas in mind.
It's going to be for Department of Defense installations, is my understanding, for the most part. So that might include Army Corps, of course. But I think that's changed a little bit now, even with the Biden administration. They're taking another look at it. I'm not sure what the threat is exactly. I understand telemetry is being, probably visible, but beyond telemetry, is there a potential for image leaks? I don't know. I can't probably speak to that cybersecurity stuff too well, but I have to say DJI products engineering is just awesome. The stuff is so easy to use and deploy. And that's what I fly exclusively.
That's probably why it's so popular too.
Yeah, ease of use. Yeah.
Any other questions on the Zoom?
Yeah, I've got one more. I think tips on how to get started if you have some GIS experience and some drone experience. I would say you would want to find your wheelhouse. What is it that you're not just interested in, but have experience in? So that may be, for me, it's environmental science. I think you become a lot more dangerous person when you can take your academic background and use drones simply as a tool to get better information for whatever you're curious about. So if you're interested in infrastructure and transportation, just focus in on that. If you're interested in some forestry, then you probably want to start, getting into LiDAR and even hyperspectral imagery. I'm not sure if that's helpful or not, but I would say, yeah, just really try and focus in on what you do best and use those GIS and drones as just tools to enhance what you're already doing.
Pix4D is not free though, right? Are there free open source options for that kind of?
Open source, I'm not familiar with any open source. I don't know if QGIS has any sort of module that could process data, but Pix4D is, yeah. And the softwares for structure for motion, I think are getting more expensive, actually. You folks are lucky, you get some academic pricing. No.
Oh, yeah, we
We do.
do, absolutely.
I think it's still.
I think the professional version is around 3,500 and we pay 500.
Oh, okay.
Yeah, that's going to depend on how many licenses you have, probably the seats or whatever they are. But yeah, they're not cheap. You've got ArcGIS, which is a drone to map, but my understanding is the backbone for drone to map is actually Pix4D. Global Mapper,
We have that.
that's a little bit more affordable than the other software, such as Agisoft or Pix4D. I don't know about its performance. Pix4D gives you lots of options, which is nice, and accuracy reporting. Yeah, you just have to see what works best for you. They're trying to think of drone deploy. They have some tools, but I've always been sort of wary of drone deploy in terms of its accuracy and accuracy reporting. Yeah, but I think, I haven't looked at it in a number of years, so it's probably improved quite a bit as well. User friendly.
Any other questions or comments?
Yeah. Plus they may be questions.
All right, well, thank you very much, Stefan, and thanks everyone for joining us. Appreciate it.
Thank you.
Or you have to advertise the moving on, tell them about the next one. Wait, the next.
Yeah, they got the.